Okay, so welcome to the problem-solving session of gravitation. So today I will solve some problems which we asked during the last years, and I will solve them explicitly and show you how the problems are solved in the chapter of gravitation. Okay, so let me start by solving the first problem which we asked. You can see it from here, but let me read it to you. It says, suppose you want to place a weather satellite with a mass m into a circular orbit of altitude of RE divided by 10, where RE is the radius of the Earth. So you take a satellite and you just place it to a height of RE, which is the radius of the Earth divided by 10, above the surface of the Earth. Okay, and then it's asking a couple of questions, which is 10 to 13. So I will start with 10. So let me draw the picture first. So it looks like that, where the radius is RE, and you take a satellite and probably you throw it like that, and eventually it goes on, just follows the circular orbit, okay? And this height which we reach, so I'm going to call that h. H is given in the problem as RE divided by 10, okay? And here RE is the radius of the Earth. Radius of the Earth. Okay. And then the problem tells us that take this following parameter, which is lambda equal to GME, G is Newton's constant, divided by radius of the Earth. So lambda is defined to be a parameter which is constant, which is equal to Gm divided by R. So mass is ME is the mass of the Earth. So this is mass of the Earth. And RE is the radius of the Earth. Okay, for that particular situation, now the question asks us to find out first in problem number 10, what is the speed of the satellite in this orbit? So in 10, find out the orbital speed. Okay, so in order to solve that, in order for this object to stay on the orbit, and if it's a circular orbit, we know that in circular motion, and if the velocity is constant, and it is constant here, according to the question, because it's following a circular orbit where the acceleration is on the radial and it's towards the center. And the thing that causes the acceleration A is the total force along that direction. So the total force acting on this satellite, which has a mass of small m, let's say, and the mass of the Earth is ME, that's equal to mass times acceleration along the radial direction. So I'm going to put radial here. Okay, so the force acting on this is just the gravitational attractive force of Earth. So that's equal to G times small m, this is the mass of the satellite, times capital M, so that's mass of the Earth, divided by the distance between the two. So the distance between the two, as you can see, is this total distance. So I'm going to call that, I don't know, like R, with a square here. Notice that since h is given as that, R is equal to h plus radius of the Earth for this problem. Okay, I will continue writing the right-hand side of the equation, which is m times radial acceleration is given as v squared over r. So you see that m's drop out and r cancels, the small r's cancel each other. And now we have an equation only for the orbital velocity VO. So VO squared is equal to G, mass of the Earth, divided by the radial distance between the center of the Earth and the object, satellite, which is satellite. Okay, that's equal to, and here let's note that R is H plus RE again, and this is H is RE divided by 10 plus RE is equal to 11 over 10 times RE. Okay, now we are ready. We can basically take that and plug that R value in here. So that's G times mass of the Earth divided by the radial distance is 11 over 10 times RE. And that's equal to, so this 11 over 10 is going to go up to the denominator as 10 over 11 times G mass of the Earth divided by radius of the Earth. So the problem tells us here that this particular combination is called lambda, right? And therefore, V squared is equal to 10 over 11 times lambda. And from here, we find that V0 is equal to square root of 10 over 11. lambda. Okay, so that's the first problem, 10. And as you can see, it has 4 parts. Let's continue and solve the other parts. 11, it says, what is the radial acceleration of the satellite in this orbit? So what is the radial acceleration of the satellite? So that's very easy because we already here have written what AR is. That's V of the orbit squared divided by the radial distance, which is small r. So therefore, we are just going to take V0 squared and then divide that to the radial distance, right? Okay, so let's do that. So that is equal to, so V0 squared is already known. That's 10 over 11 times lambda. And we are going to divide that to r. And remember that r is equal to 11 over 10 times re. And therefore, you can see that that's 10 over 11 square times lambda divided by re. So that's the answer B among the choices. Now 12. In problem number 12, it says, what is the total mechanical energy of the satellite when it is in this orbit? So what is the total energy of the system? Mechanical energy is composed of 2 parts. One is the kinetic energy and the other one is potential energy. So we basically have to add these two to get the total energy, total mechanical energy of the satellite in this orbit. So if I write it down, mechanical energy is equal to kinetic energy plus total potential energy, right? So it is equal to then 1 over 2, and this is when it is orbiting the Earth during the orbit. So that's why it is 1 over 2 m v0 squared minus, because this is gravitational attractive potential energy, so that's why it has to be minus g, mass of the Earth, times mass of the object, divided by the distance between the two. So we just plug in the numbers. So what is that? So that's equal to 1/2 m. And we already know what v0 squared is. It's right here. And let's just put it. So that's 10 over 11 lambda minus, and that's g times mass of the Earth times m divided by, r is, again, 11 over 10 radius of the Earth. So if we just add them up, we get 5 over 11 lambda m minus. So from here, I get 10 over 11 again. If I take 11 over 10 and take it to the numerator, I get m times g mass of the Earth divided by radius of the Earth. And as you remember, this particular combination was called lambda. So that's equal to 5 over 11 lambda m minus 10 over 11 lambda m. And if we subtract one from the other, we get basically plus 5 coming from here, minus 10 coming from here, divided by 11 lambda over m. So that's the multiplicative factor in front. Subtract one from the other, we get minus 5 over 11 lambda times m. So that's the total mechanical energy of the system, which is choice, which is E, right? Okay, so the last part of this problem is 13. So let me read it first. How much work has to be done to place this satellite in the orbit? Okay, so it is asking for how much work done. So here, notice that it doesn't say how much work is done by gravitational force. It says how much work done to place this. So how much work done by an external agent, let's say, by an external agent, to place this to the satellite. So you notice that the mechanical energy is constant. That's constant. So that is the final energy, which is 5 over 11 times lambda m, right? That is the constant energy. So even at the beginning, we have to create this constant energy. And how do we do it? We have this potential energy when the satellite is on the surface of the Earth. Let me write it like that, Re. So the initial potential energy that we have is minus, this is m, this is capital M-E, minus g times mass of the Earth divided by radius of the Earth. So that's the initial potential energy. And this potential energy basically plus the work that we do basically is equal to, has to be equal to minus 5 over 11 lambda m, because that's the final total mechanical energy that we have. So therefore, minus gm over Re, which is multiplied by m, which is lambda times m, is equal to potential energy that we have. And if we take that, and if we add work to that, we have to get minus 5 over 11 times lambda m. And that tells us that minus lambda m plus work done by us is equal to minus 5 over 11 lambda m. Therefore, work is equal to lambda m minus 5 over 11 lambda m, and that's equal to 6 over 11 lambda m. And that's choice number C. Okay? So these are the first 4 problems related to the gravitation chapter of this final exam of January 8, 2018. Okay. Now I'm going to solve the other 3 problems, which is another set of problems, questions 14 to 16. So let me read it first. It says, consider a ring-shaped object which is uniformly distributed in the figure, as you can see from the figure. A particle with a mass m is placed at a distance of x from the center of the ring, along the line through the center of the ring and perpendicular to its plane. As you can see from the figure, an object is placed right on top of the middle of this basically ring-like structure, where this is m, and the radius of the ring is r, and the mass is capital M, okay? So then it asks basically 3 questions. The first one is it's asking for the potential energy of the system. That's 14. And 15, it says, what is the force exerted by the ring on the particle? And then the final one is, what is it when x is large enough? So let's start with 14 first. What is the potential energy? That's very easy, because you can see that if it's a ring-like structure, and if this mass is just above the center of the ring, then all of the distances are exactly the same. So what I have to do is, I just basically take the effect of each small part. Since they are all at equal distance from small m, the distance is basically, this distance is r, and this is at the height of x, and that's why this distance is x squared plus r squared with the square root, right? So that's equal to like s. So therefore, the potential energy between small m and capital M is minus g times small m times capital M here, divided by the distance, which is x squared plus r squared with the square root. Okay, so that's 14, and this is choice D, right? Okay, that's 14. What about 15? 15 is even easier, because we know that gradient of u with the negative sign in front gives us the force. So what we are going to do is we will just take the derivative of that. The direction of this is obviously, it is attractive, and that's why it is towards the center. And since it's towards, you can just attribute a sign, but here it's just asking us the magnitude of that. So that's why we don't have to worry about the minus or plus sign, we just have to take the derivative of that. And as you can see, the gradient is actually kind of a 3-dimensional derivative, but here, since it only depends on x coordinate, we can just take gradient to be d over dx. And then take the derivative with respect to, of course, this is I, if this is gradient. But here, the direction doesn't matter, because we are going to take the magnitude of that. So that's why even direction is totally irrelevant. We're just going to take the derivative with respect to x. So I'm taking d over dx of minus g m times capital M divided by x squared plus r squared with a square root. So if you take the derivative of this combination, since g, small m, and capital M, they're constant, they will go out of the integral. That's m, and d over dx of x squared plus r squared with minus 1/2. You take the derivative of that, and first minus 1/2 goes to the front, so that's minus 1/2 times minus gm capital M, and you take the derivative of the thing which is inside, so this is r squared, right? And that will bring a factor of 2x, when you take the derivative of the thing which is inside. So you take the derivative of the function first, and then you decrease this power, minus 1 over 2, by 1. And minus 1 over 2 minus 1 is minus 3 halves. And that's why this becomes x squared plus r squared with 3 halves. So from here, you see that minus cancels the minus, 2 cancels the other 2. And we get g, m, capital M, divided by x squared plus r squared with 3 halves. So that's B, right? B is the correct choice. Okay, so we are almost done. Now the next thing is basically even much easier, because let's read it again. It says, what is the magnitude of the gravitational force exerted by the ring on the point when the particle is very far away from the ring? What that means is, when x is much bigger than r, what happens to this force that we just calculated here? So when x is much larger than r, then x squared plus r squared, and there is an x here, sorry. So this becomes approximately equal to x squared with 3 halves, right? Which is nothing but x cubed. So the magnitude of F is equal to g, m, and small x. That doesn't change, right? So we just divide that to basically x cubed. So that cancels that, and we get g, m, capital M, divided by x squared. So that is the magnitude of the gravitational force exerted by the ring to the point when it is very far away. And you can see that this looks exactly like the interaction between 2 point particles when they are separated by a distance of x. And the reason is obvious, right? When you are very far away from a ring, you will not notice the difference between a ring and a point, and that's why the formula is basically g times mass of one of the particle times mass of the other, divided by the distance squared between the two. Okay, so today what we did was we solved the January 8, 2018 final exams question related to gravitation, and thank you for listening.